Dr. Tomple and still actually has an appointment with Louisiana State University as a professor of environmental chemistry. And with that experience and background, he'll be discussing for us today pathways of exposure. Dr. Tomple.
Thank you. It's nice to be here. It's especially nice that I don't have to talk about the EQ today. I'll talk more about things I used to talk about at LSU, which is actually more fun than talking about the EQ. Let me dispose of the EQ role pretty quick. EQ's role, as I see it in one sentence, is to reduce the contaminants in the environment to the lowest possible level. Although we know that zero may not be achieved. What I want to talk to you today about is what happens to chemicals when they enter the environment. How do they affect you? How can they affect you? I won't talk about the person interface, but rather the environment interface with the chemical. To sum it up in one word, this is what we call bioavailability. There's some enormously toxic compound that's been contained. There's no way it's going to be available to you. There's no way it's going to harm you. If, however, it's released, then it's a whole different matter. It's that question of how do they become available to you? How do they reach you? That we want to talk about today. In the jargon of the trade, environmental chemistry, this is what we call fate and effects. Fate meaning what ultimately happens to it, and effects means what does it do once it's out there. You're probably aware that if there's a gas in the air and you breathe it, then you're exposed to it. You are available to it, or it's available to you. But you may not be aware that dust in the air or very small particulate matter collects things like metals, various organic compounds like dioxins and others. And if you breathe that particle, you also get those chemicals. Now, this is important because you don't expect that you're going to find metals in the air or that you're going to find some of these organic compounds in the air because the chemistry won't tell us that. So it turns out to be a fairly complicated issue, and I've got some slides and visuals which I'll use to try and explain some of that. And there are other routes of exposure that are not very obvious, at least not on first blush. So let's take a look at some of those. As chemists will want to do, we tend to take things apart and divide them up into little parts. This is reductionism at its worst, and it's probably what's gotten us into so much trouble. But it's helpful sometimes to be able to look at the parts because it's too complicated to look at the whole simultaneously. So let's look at some of the parts. These are the parts of the environment. We call them compartments. And starting from this side, this is the pollutant of any type that we throw into the environment. That's what the dashed lines indicate. And compartments are air, soil, and of course sediment has to be included in the soil, and water on this side. The smaller language in here deals with various processes that go on in those compartments. The lines between them are transport mechanisms which show you how the chemicals move from one compartment to another. And I have some data which I'll show you, and you get some idea of how you can use this information to tell where a chemical will end up. That's what we're really interested in. Fate of it. Where does it end up? If I take a handful of PCB and throw it into the floor of the stage here, where ultimately, when I come back in a year, where's it going to be? Turns out PCB doesn't have too much vapor pressure, but it's got a little, so some of it's going to be in the air. Most of it's going to stay right there. If you throw it in the water, it's not really soluble in water. It's got a little bit of solubility, but mainly it's going to attach itself to some particles in the water and fall into the sediments. So as a chemist, if I go out and I'm looking for PCBs and I analyze the air, I'm probably not going to find any, even though there's tons of it around. If I analyze the water, I probably won't find any, unless I catch some sediment particles, because that's where it's going to be. If you analyze the bottom of the stream, however, that's where you will find it. So it's important to know where these compounds will end up, what their fate will be, if you're out analyzing these kinds of compounds, and if you're worried about people getting exposed to them. Now, if that same PCB is on the bottom of the stream, then you say, okay, well, it's not really available to me, it's not going to hurt me. Well, turns out there's plants that grow down there, and these plants pick it up, and that's what we call bioaccumulation. And once those have it, then the catfish will eat it. It gets in the catfish, it goes up to some level. You catch the catfish and eat it, and then by a food chain mechanism, you become exposed to that same PCB, which we thought wasn't going to be a problem, but it didn't seem to have much volatility, it didn't seem to have much solubility, so we thought it was going to end up in the sediments. Doesn't always work that way. For many years, we thought that dilution was the solution to pollution. That is, if we threw something into the environment, second law of thermodynamics seems to tell us it's going to disperse itself through the environment. It's no longer the case. We know now that accumulation occurs, that things actually can concentrate in the environment. Rather than becoming more dispersed, they become more concentrated. It's usually organisms that do that concentration. We'll talk about that in a minute. These, in case you can't read them, for instance, this is soil and sediment. If we throw a pollutant down into the ground, if it's got some volatility, it'll volatilize into the air. And then, I almost volatilized off the stage. Then the air becomes contaminated. If, however, it doesn't have much volatility, but it has a desorption capacity, then it'll go into the water, and then it assumes that it's got some solubility in water. If it's in that water and it's picked up by some organism, this is the biota representing all the organisms, then it will be concentrated in that organism. When we talk about organisms over on this side, we've got to be aware of a number of different things. There's a couple of factors which contribute to bioaccumulation. One is the life of the compound. I'll talk to you about half-lives. I have another visual to show you. The half-life gives you some feel for how long the compound will be around. The half-life, for instance, tells you if you've got a pound now, how long will it take until you've got only a half pound. Some compounds, like DDT, that life can be 10, 15 years. So you've got some long-lived compounds and you've got some short-lived compounds. The short-lived ones usually are natural kinds of compounds. They're degraded usually by bacteria, although sunlight can degrade compounds. But the man-made ones, the synthetic, especially the chlorinated hydrocarbons, are fairly long-lived compounds. I think this is my own theory, so don't test it on the textbooks, but my feeling is because they're synthetic, man-made, they are rarely seen on Earth except since we've been here. There are no organisms that evolve with these compounds to degrade them. As you probably know, every compound created by nature is easily biodegradable because nature works in cycles, and those cycles have to continue to go, which means that the decomposers have to be able to remove that compound. Well, there are no decomposers, no natural decomposers for many chlorinated organics. That's why they last, one reason they last so long. The other is that their bond strength is very strong. My apologies for some of these chemical terms, but it's difficult to discuss this subject without getting a little bit into chemistry. So this is what the environment looks like from a chemist's point of view. I agree it's not a very pretty point of view, but it's functional. And it tells us a number of different things. So remember these compartments, which are important, and that there are pathways between each of them to allow a pollutant of some sort to move from one of these compartments to another, and that there's some time factor involved in it. There's also some degradation processes going on, usually bacteria-driven, the decomposers of the molds, the fungi, and bacteria. And thank God for them, because we'd be up to our elbows and everything if we didn't have these kinds of decomposers around. Left are the compartments again, air, water, and soil. In the middle are some of the transport mechanisms that are important. And of course, we're dealing with air. You're really talking about meteorological transport. The winds become important. I've got to know something about the winds. We do modeling, for instance, in the deep. We figure out where the latest spill of vinyl chloride is going to go. There are diffusion and dispersion. I won't go through all of these. You can see them. For instance, in soil, leaching is very important. Leachate is something I'm sure you know that comes out of landfills. So there's a mechanism of water leaching things from soil as it moves through them. These are the transformation processes that go on in each of those compartments. Photolysis, oxidation, these are chemical reactions. This one is probably one of the most important, the biodegradation by bacterial metabolism. Extremely important for removing various compounds from our realm. We don't want them around. It's great to have those bacteria to take care of them for us. And a little bit of more of the same. Here's some of those same transport mechanisms. And here are the things that we measure, the properties that are important in controlling those. Again, if we're talking about meteorological transport, then we've got to know wind velocity. If we're talking about biouptake and biomass, the amount of the organic decomposer that's there is important. Leaching, for instance, absorption coefficients are important. How fast do those chemicals come off of the soil particle? Enough on that one. It's a little dry slide. Now, if you're a chemist sitting in your office and you know that a spill has occurred, there are a number of ways to predict where that spill will end up, where that chemical will end up. These are some physical chemical data that we use. Molecular weight, you don't need to worry about that. And by the way, I'm going to make a general comment. You won't be tested on this. It's not necessary that you memorize this. It is probably important that you know that there are techniques for doing this. You can find them in the library or the textbooks or talking to somebody at your local university. Kinds of things that are important are like solubility. That's how much of it will dissolve in water. Is the vapor pressure. That tells you how volatile it is, how much will it end up in the air. And over here is the transfer coefficient. It tells you how fast it moves from, in this particular case, I think it's water to air. Let's look at one that you may know something about. Here's some chemicals listed side here. Benzene's everywhere. It's in gasoline. When I was a chemistry student, we used to wash our glassware with it until we found out it was very dangerous for us. Sure, we'll pay for that one. But for instance, you throw some benzene into the environment. Let's say we spill it in the river. What's going to happen to it? Well, the solubility is fairly high. It's just the range of these numbers I want you to look at. You don't have to know exactly what they mean, but that means it'll be a couple of thousand parts per million in the water, about 2,000 maybe. These are dependent on chemistry. That's a detail you don't have to worry about. But it also has a high vapor pressure. In fact, it's the highest in this list. This is scientific notation. The -7 means it's very, very low. And the transfer mechanism is pretty fast. So if benzene goes into the water, and it does here in Louisiana occasionally, we know that some of it will remain in the water, but the biggest portion of it will wind up in the air that we'll be breathing in. And that's why particular kinds of compounds that spill are very bad. Pesticides, let's take a look at DDT. It's got a high molecular weight, it's got very little solubility in water, so if you go out and analyze the water after DDT spill into that same water, you won't find it floating in the water. It's not very much there. You may find a very tiny amount. When I see a very low solubility, I know though that it's probably going to go in the sediments or it's going to go in the air. Well, will it go into the air? No, not really. This is extremely low. No reason to expect it there. The transfer coefficient is very low too, so it won't move from the water to the air. It'll go down into the bottom of the stream, and that's where you look for DDT. So this tells us then how things become available to us, what the routes are. So it's down in the sediments, not going to do us any harm, right? No, wrong. The organisms that are down in those sediments will pick it up and accumulate it. We'll get to that in a minute. So we do have to be concerned about things like DDT. The PCBs down here on the bottom, very low solubility in water. This one's got a little bit, but not much. Very poor vapor pressure, very low vapor pressure. It won't go in the air. It tells me it's going to wind up in the soil. It's going to wind up in the sediment somewhere. It won't evaporate in the air, except very, very slowly. And it won't stay in the water. So it'll be down in the sediments. I mentioned to you that life of the compound is important. If it's going to stay around a real long time, then we've got to be more concerned about it than if it's got a short lifetime. Some of the early pesticides, the organochlorines, and this is a list of them, have very long half-lives. 10 years maximum for DDT. That means that half of it will be here in 10 years. We normally say that you need about 10 half-lives to get rid of something. So we're talking about 100 years to see DDT around. So that one we need to be concerned about. This also is important in the bioaccumulation, and along with another factor which I'll explain in a minute. The organophosphorus compounds are much shorter lived. They're much more acutely toxic, which I'll show you in a minute, than are these, but they don't last very long. Oh, 1/10 of a year, 2/10 of a year. So a month after you spray them, you won't expect to find them in the environment. They're decomposed. The reason they're decomposed, they don't have this carbon-chlorine bond. The carbon-chlorine bond is a very strong bond. And there are organisms and natural compounds that are organophosphates in the environment. So we know that we don't want to expect to find these. Now, if you're handling these in large quantities, you can expect to be killed very quickly if you mishandle them. Maybe that's a kind of natural selection process there also. Not the kind I recommend. But you handle these, I think you tend to get cavalier about them. You've probably seen the guys that says, well, I'll eat a pound of DDT and it won't do them any harm. And it won't do them any short-term harm because it's not very acutely toxic. It does have some long-term toxicity. A little bit more of the same, but expressed slightly different. Here are some different kinds of compounds. Here's the persistence, that is, how long they will live in the environment. Here's the process that gets rid of them. Most of these bacteria are driven, although some of them may use sunlight. Photolysis would be sunlight. You don't see any photolysis there, but things like the benzoic acids we expect to see around for a year. Carbamates, 2 to 8 weeks. Urea is 4 to 10 months, because urea is a natural. They're in the environment already. They're part of our biological process. So they don't last very long. There are bacteria that will take care of them. And the last slide. Here are some things that contribute to that bioaccumulation I mentioned to you. There's 2 factors important in bioaccumulation. One is the life of the compound, how long it will live. The ones that live longer tend to bioaccumulate more. Secondly is what's called the octanol water coefficient. Now, octanol is a compound that's very similar to a fat. It's the same fats that are in our body. Water, you know what it is. So if we take a beaker and put half water, half octanol, throw a chemical in there, shake it up, we can measure what goes into the octanol, what goes into the water. That tells you how soluble, it's called lipid soluble, how soluble they are in our fats. If something is soluble in fat, you can be reasonably sure it will accumulate in our bodies. That also means it's not soluble in water, and what they're showing you here is that something that has solubility in water, there's very little bioaccumulation that goes on because our body uses the water mechanism to get rid of various compounds. If it's not soluble in water, and DDT is not, we're talking about a bioaccumulation factor of 1 million. That's a lot. So the classic case happened in California where they sprayed some compound, and let's just take a unit 1, arbitrary unit. They found 265 times that amount in the plankton. This is to get rid of a flea out of Clear Lake, California. Not a flea, but a little water gnat, which was irritating tourists. And got into the plankton at 265 times the amount in the water, got into the small fish at a 500 magnification. The predaceous fish, the ones at the top of the food chain, at 85,000, and the birds at 80,000. Then, of course, it wiped out the birds, and you know that whole story. This is the first time we found, at least I think it's the first time we found that that dilution no longer worked, that some opposite things were happening, and in fact we found a concentration factor going on when we thought it was going to be diluted into the environment. They sprayed this in a very small amount. It was in the parts per billion range to start off with, but it got concentrated very fast. And it's related to this, to the lifetime. Solubility in water and the lifetime, those 2 factors. Finally, here's a chart that shows you some acute oral toxicities. These are the LD50s, the lethal dose at which 50% of the organisms die. The organic organochlorine compounds takes quite a lot to kill half of the organisms. The organophosphorus is much more toxic, it only takes this much to kill, and the carbamates are much more toxic too, but I still have a fonder feeling for these because they don't last as long in the environment. They're not really subject to bioaccumulation because they don't tend to be soluble in the octanol when we do our test on the octanol water, and thus they're not soluble in the fats. That's basically what I wanted to tell you about